So in the previous section, 3.3, we were looking at the first derivative and looking at what information regarding the function it told us. And remember, it told us a couple things. It told us, first of all, where the graph was going uphill and where the graph was going downhill. And then we could use it also to determine the locations of our local extrema, which is pretty darn cool. So in this section, we're going to kind of do the same analysis for a function f of x, but instead of looking at what its derivative tells us, we're going to look to see what information, if any, its second derivative would tell us. So that would be analogous to, like, does the acceleration tell you anything about the position of the object? Because the velocity does, right? The velocity tells you if the position is increasing or decreasing, if it's going left or right, and by what amount. The acceleration doesn't tell us, though, how the positions are changing, does it? It's the acceleration is the rate of change of what? The velocity. So it tells, the second derivative will tell you how the first derivative is changing. That's one of the things it does. It does two things. It tells you how the first derivative is changing. But it also manifests itself uniquely also on a graph, and we're going to see what that is. So it does tell you something about f itself and not just how fast f prime is changing. All right, so example 1. Let's say that we have a function such that f prime is greater than 0 on some interval. We want to draw 3 different ways in which the graph of f might appear on this interval. And in each case, we're going to see how it's increasing. So I'm just going to come right out of the origin just for simplicity's sake. You have a function that's increasing. It could increase like this. That would be increasing at a what rate? The graph's going uphill, right? So the derivative is positive because the y values are changing. But are the slopes changing? No, it's a line. What do we know about the slope of a line? It is constant. So it's increasing at a constant rate. Do we need really calculus to evaluate those things? Not necessarily. It could also increase like this. These y values are increasing, so the derivative is positive. These y values are increasing at an what? Increasing rate. They're increasing at an increasing rate, which means as you go to the right, the graph is going up steeper and steeper and steeper. So whenever you say the graph is increasing, you're talking about the first derivative. When you talk about the graph increasing at an increasing rate, you're talking about the rate of change of the derivative. This would be the second derivative. Okay? And the other way, of course, would be for a function to increase like that. Y values are going uphill, but this one's increasing at a what? Decreasing rate. So, again, in each of the 3 cases, dy dx, y prime is positive because the y values are going uphill. But it's how it's going uphill that differs. So if we looked at the tangent lines, when I look at how the tangent lines are changing, let's go ahead and write this down here. The tangent lines are going to equal y prime. The change in the slopes, which is the tangent line, is going to equal y double prime. Would you agree? Every time you take the derivative of some quantity, you're looking to see how it changes. If y prime represents the slopes or the tangent lines, then y double prime will be the change in those values. Maybe I should just say slopes. That way we're using the same word, but they are interchangeable. Okay, so if we look at the tangent line slope on the line itself is its own tangent line everywhere. So what do you think the value of the second derivative is going to be there? 0. Good. F prime, oops, I wrote that wrong, sorry, I'm thinking ahead. F prime is greater than 0. I'm not going to even use use of x, but F double prime is equal to 0. The slopes are positive, but the slopes aren't changing, so the rate of change of the slopes is 0. So the second derivative everywhere should be 0. If you ever see a second derivative equaling 0 over an interval, that function is going to be linear. Anytime the second derivative on an interval is going to be 0, that means the slopes aren't changing, it's going to be linear. Okay, over here, I know that f prime is greater than 0 because the y values are increasing. Well, let's look at what the tangent lines are doing. It's positive small there. It's positive bigger there. And it's positive even bigger there. What's happening to your tangent lines? They're increasing, okay? So when it's increasing at an increasing rate, that means not only are your y values increasing, but your slopes are increasing. So what should the second derivative be? Greater than 0. Yes. Anytime your second derivative is greater than 0, your slopes are increasing. And notice, well, we'll notice other things later. There's a lot to notice. There's a lot to notice. Let's look at the slopes here. Pretty steep, positive. A little less steep, positive. And even less steep yet, positive. Slopes are still positive, but are they increasing or decreasing? Now the slopes are decreasing. So f prime is still greater than 0, but now f double prime is less than 0. Okay, notice the 2 on the right compared to the 1 on the left. When the second derivative is 0, the graph is a straight line, linear. When the second derivative is either positive or negative, our graph is not a straight line, but rather a what? Rhymes with nerve, starts with curve. Yeah, the graph's curved. So anytime you have a graph that's curved, you're going to have a second derivative value that's not 0. In fact, the second derivative tells us what the curvature of the graph is. Okay? The curvature of the graph is going to be determined by the sign of the second derivative on an interval. Now, we refer to the curvature of the graph and another term interchangeably. Not really. It's not. Okay? Concavity. In science, you talk about concave up and concave down. Or maybe you don't talk about that. You talk about concave and convex, right? Concave, convex. That's going to be in relation to which reflective surface you're looking at. If you're looking on the inside of a dome, that would be concave. If you're looking at the outside of that same dome, it's convex. Okay, so it's reference to your position. We're not going to use convex and concave. We're just going to talk about concave up, like a cup.
Teachers, please turn your TVs to channel 4 for the morning announcements.
And concave down like a frown. Concave up like a cup, and concave down like a frown. Okay? So anytime you have a second derivative that is positive, we're going to say your graph is curving upwards. Okay? It has positive curvature. We're going to say it's concave up like a cup. Anytime your graph is curving downward, oh, that's over here. I was going to the screen. Too big. Anytime, that'd be cool. Smartboard maybe. Anytime your graph is curving downward, your second derivative is going to be negative, and we say the graph is concave down, like a round. This class is almost over. Okay, here we go. Important idea. If the first derivative tells us the slopes, whether the function is increasing or decreasing, the second derivative now tells us the what of the graph of f? The concavity, the curvature. So now the second derivative means two things. It tells you, of course, how the slopes are changing, but it also tells you the curvature of the graph. All right, and you can read this if you want, but I have some memes. Is that what you people call these days? Memes. Here's an easy way to remember the curvature or the concavity. They're interchangeable based upon the sign of f double prime. Okay? When your second derivative is positive, right? If you have positive plus signs in your eyes, you're probably pretty what? Happy. I would guess you're happy. If I saw someone with 2 plus signs in their eyes, they would probably be smiling and I'd probably be running because that would be weird. So concave up like a cup. Now notice any part of the smile is going to be concave up, right? It could be this part of the smile or this part of the smile. So it could be decreasing, the graph could be decreasing concave up or increasing concave up. As long as it's part of a smile, it's going to hold water like a cup, it's concave up. And the second derivative will be what? Positive. Got it? Okay, cool. And then, of course, concave down like a frown. And every time I think of a frown, that's who I think of. That's, what's his name? Walter. Yeah, Walter. Okay. The perfect concave down like a frown. So, again, it could be any part of a frown. It could be increasing concave down or decreasing concave down. That feels weird. Trace over his lips there. Oh, Walter. And putting some chapstick on him there, Walter. All right, so increasing concave down or decreasing concave down? All right. Got it? And then this one here, that's supposed to be a horizontal line. 0, it's not quite there. But it doesn't need to be a horizontal line. It doesn't need to be a horizontal line, as long as it's a what? Line. Maybe I meant to put it slightly out of horizontal, because it's kind of, yeah. Anyway, if there's no concavity to it, it's going to be a straight line. It has curved depravity. Or we call it linear. Okay, so notice the zeros in his eyes. Those are round zeros, right? Zeros. So if the second derivative is 0, then it's going to have 0. Oh, I didn't make that reference over here. Concave down like a frown is when the second derivative is what? Positive or negative? Negative. And notice Walter is squinting, so his eyes are kind of beady like negative signs. So negative second derivative, concave down like a frown. Positive second derivative, concave up like a cup. Saucers for eyes, 0. Curved depravity. Okay, it's going to be linear, no curvature at all. Easy to remember, right? With memes. Speaking the language of the teenagers. All right. Determine the signs of f and f prime for each of the curved segments below. Fill in the inequality. Okay, so we're missing some inequalities. This is a circle with parts of it whited out. Okay? Because here's the cool part. If you know the sign of the first derivative and the second derivative of any function on any given interval, you know what it's doing. It's going to be one of these 4 things if it exists at all. It's going to be one of these 4 things. Okay, let's look at this. Let's look at this top left segment. If we read this from left to right, and we just think about this top left segment, this would be increasing concave what? Down. So the first derivative should be what in relation to 0? Positive, thank you. The first derivative tells you what the y values are doing. The y values are going up. The slopes are positive, so the first derivative is positive. It's concave down like a frown, so f double prime is negative. Okay, now notice if it is concave down like a frown, your tangent lines are where in relation to the curve? Above or below? Above. Above the curve. That's kind of an important thing that'll come into play later. Just a nice observation now. And another observation, your secant lines are where? Okay, your secant lines are below. You could always draw that if you weren't sure. Okay, let's look at this next segment. From left to right, this function is going downhill, and it's what? Concave down or concave up? It's concave down. So because it's decreasing, the first derivative is negative, and because it's concave down like a frown, the slopes are decreasing, and the second derivative is negative also. Any part of a frown. Okay, now let's look at the tangent lines here. The tangent lines, would you stop being so moody? Okay, notice your tangent lines are still above, right? It's concave down and your tangent lines are above the curve. And your secant lines are still what? Your secant lines are still below. And that has to do with the concavity. Notice anytime your graph is concave down like a frown, your tangent lines will be above and your secant lines will be below. Now it's kind of weird to say here that the slopes are decreasing, right? Because they're getting steeper, but in the negative direction. Absolutely. Very good. All right, let's come down here to the bottom left. If we read it from left to right, the y values are getting smaller, so the first derivative is less than 0 or greater than 0. We're decreasing, aren't we? So first derivative is less than 0. And is it concave up or down? Concave up. So the slopes are increasing, and the second derivative is positive. Good. So if you look at your tangent lines, now your tangent lines are where in relation to the curve? Tangent lines are below the curve because it's concave up. And notice the slopes are increasing. They're becoming less negative. Does that make sense? And the secant lines are where in relation to the curve? Above. So everything's switched now. The secant lines are above. And then the last little thing we'll do here today, increasing concave up, f prime is greater than 0, f double prime is greater than 0. So the y values are getting bigger, but so are the tangent lines. Notice the slopes are getting steeper. Tangent lines are where? They're still below, and the secant lines are still where? Above. So you might have to use your concavity in the near future to determine if an approximation using the secant line or the tangent line is too big or too small. And it comes down to, well, is the tangent line you're using above or below the curve based upon the concavity? If your tangent line is below the curve, then your approximation is going to be too small. If your tangent line is above the curve, your tangent line is going to be too big. Okay? So notice that every time the graph is concave up like a cup, your tangent lines are below, and every time your graph is concave down like a frown, any part of a frown, your tangent lines are above. Okay, we'll define another term on Monday. Just real quickly here, the first derivative gives us what of the graph? Slopes, and the second derivative gives us concavity or curvature. Okay, very good.